All right, good afternoon, folks. It is May 26th, so we are almost into June. We had our first week of classes last week. We did have some people who joined late, so welcome to those of you this week as your first week. Make sure that you hang out after we're done working our problems today if you have any questions and making sure you get caught up in the course. But today we're going to keep it nice and relaxed because we do have some new people and we are virtual only today. And we're going to go easy and work some problems. And we also will be making sure that you all have another chance to form your teams. So after today, you all are going to have to work in your teams together to solve problems, and we'll have friendly competitions. So definitely appreciate the slow pace of today before we get on with more exciting things. So we have, let's see how many we've got. All right, looks like everybody is in here pretty well. Okay, perfect. And I can see the chats. All right, we will get started. Oh, we have a hand raised. Go ahead. It looks like, who do we have? We have Joel has a question, so go for it.
Is this class being recorded? And if so, is it going to be on campus?
No, nothing is in Canvas for the recordings because they're all done through Teams. So you can find Teams recordings in your Teams. So no need to go to Canvas. You will go to Teams for all of your recordings. So I will show you a couple things right now so that you are aware of what they are. So thank you, Joel, for your question because you all will want to see this as well. All right, so I will bring over your other Teams window. So you'll notice that Teams usually opens up into two windows. So you'll notice that right now that we're in the general channel, and that's where all of our class sessions that we do together will be. So you'll notice here was our virtual only for today. You'll notice here was our first class session together. So that's the general channel where we find all our class meetings. Then you'll notice that there is an office hours channel. Woohoo! So if you click on that, you will notice that I have a meeting set up for every Tuesday from 5 to 6 p.m. So when it's that time, so the first one will be this evening. So if you're having any problems with the problems that we go over today, please come see me. Or if you need to just ask any other questions about the course, that's what I'm here for too. Now, as you get your TAs, they will also have their own channels, so you can pop into their times for office hours and be able to see them too, because then they'll be able to offer more hours than just me alone. So be checking out these different channels that you have. The other cool thing that will pop up later is that each of the teams will be provided with their own private team channel that only your team will be able to access. So that's a cool way for you to be able to collaborate, and you'll need it for our team problems together, and you'll need it for your team project. So we're going to be going over that at one more time once those have been formed, but you'll see the Teams channels pop up under here too. So lots of good stuff to be found in Teams. Now, to Joel's point, if you click on the general channel, and then you go up to the top, you'll notice there's some different menu options. And then you would go under the shared menu option here at the top, and you'll notice that there is a folder with recordings. So it'll be up for you to find the correct recording for the class that you missed. But I do not post them in Canvas because they're already all right here and you have access to them. Okay, so let's go back to our other view. See if there's any other questions. Let's see. I don't see anybody else's hand raised. All right. So we'll get to our main content for today. So how many of you know how to find the problems that we're going to be working on any given day? Does everybody remember how to do that? Let's see. Any other questions about people who entered late or having issues with their own assignments that you'll want to come see me during office hours or at the end of class? Let's see, but the course schedule, yes. So good job for those of you who know. So please make sure that you consult in your Canvas course. You have a whole first module that has really important information. So it has your syllabus, it has your course schedule, and it has your linear system exam dates. And it also has your office hours with me. So that's a great place to look for just general information about the course. But for our course schedule, if you've looked at that already, hopefully you guys have reviewed your content videos. I am counting on you to do that as part of a flipped classroom setup. Please make sure you have reviewed your content videos because today we are jumping into our problems. And we're going to apply all that knowledge from our chapter section. So the content videos were on chapter 1, sections 1.1, 1.2, and 1.3. So everybody should have a very good idea of what a matrix is. And we're going to go ahead and switch on over. That. And here we go. So for our section 1.1, we have problems 1, 5, 7, 9, 10, and 11. So my first question for you all, just as a little trivia question, is who knows when they first think that the first augmented matrix was used? How long ago? Anybody know? How long has humankind been using some sort of form of an augmented matrix? Does anybody know? Oh, we got a guess in there, 1800s? Well, actually, we've been using a lot of these mathematical concepts a lot longer than that. Somebody else says BC. Yeah, it was definitely sometime BC. Long time ago. Oh, we got another guess, 800 BC. So good guess, it's BC. Overshot it a little bit. Oop, Keegan's got more of our estimate here. So yeah, 200 to 100 BC. Humans started using some sort of form of augmented matrix. So the whole idea was out there long time ago. Okay, so we're going to go ahead and we're going to jump on our problems here for section 1.1. So the first thing we had to establish with this first section is what in the world is even a linear system? What are linear equations? So your linear system that you're trying to solve for is going to be a set of linear equations. So who can tell me what a linear equation is? That'll be your next trivia question. Who can tell me what a linear equation means? How do we know we're dealing with a linear equation? Don't be afraid to use your mics as well.
All the variables occur into the first power.
You got it. All right, nicely done. Yes. So they're all to the first power. So here's going to be your first test here. Here in this problem number 1, we're going to be looking at, it says in each part, determine whether the equation is linear in variables x1, x2, and x3. So you'll notice that they decided to use all the letter x for the variables. They're going to be using subscripts here, 1, 2, and 3 to denote the different unknowns. So what do you think about A? What do we think? Do we think that's a linear equation? All right, we've got Oh, we got some no's and yeses. Okay, well, hopefully we see that it is a yes, right? So here x1 we have that's to the first power. Its coefficient is 1. Here we got 5x2. That's also to the first power. Here this was a little tricky. You can have a square root as long as it's the coefficient before your unknown. So here, because the square root of 2 was your coefficient, your unknown was still only to the first order, first power. So all of that will be a linear equation. All right, so B, what do we think there? What's going on with that one? Oh, we got a, that was a quick no. That's right. So B is no. All right, anybody want to know who can say why? Anybody got an idea? Ooh, yeah, you can't have your unknowns multiplied together. So that x1 times x3, boo, no. So all of your unknowns, first power, it can't be multiplied with each other. All right, so second one, B, is no. All right, C, what do we think about C? How are we liking that one? What about C? All right, we've got a yes coming in. Okay. It's rewritten a little bit differently, but if we look at each of our unknowns, they're all to the first power. Nothing strange there. All right, let's look at D. What do we think about D? Oh, that looks like that got a quick no. What's wrong with that one? Yeah, we got a negative power. So here's the thing, you have to be careful with these. I will say this textbook is going to write your unknowns in a couple different ways, or your variables. So the thing about the subscripts that they use, you have to be really, really careful. Sometimes glancing at this, you might not realize that something is raised to a power versus like a subscript. So you want to make sure that you look at those carefully. But this one does have it raised to a -2 power, so no good on that one. E, we have the same problem. Here, E, we have this first variable raised to the 3/5 power. Let's see, let's look at F. Anything you notice about F? What would you say there? Oh, yeah, we got some yeses in there. So here's another one. Don't be fooled. Pi is still your coefficient. That's okay. Your x1, your x2, both still to the first power. That square root of 2, once again, is in your coefficient position, so no problem there. So this is also a linear equation. All right, good job, everybody. Thank you for your participation. Very cool. All right, so our next problem, we're going to jump down to number 5. But before we do that, we have some things that I want to ask you. So if you have a linear system, and which means that your equations are all linear equations to be hence called a linear system, what exactly are you trying to do with a linear system? What are you trying to solve for? So let's pretend that I have a linear system that has 3 linear equations in it, which means all of your unknowns, all your variables are only 2 raised to the first power. And you have this system of equations. What are you trying to do if you say that you're solving for that system? Anybody have an idea? Like, what's the whole point of it? Well, one of the things, we could find an intersection point. That might be key. What are we trying to do, though? We kind of look at the big picture. You'd say that you're solving a linear system or a set of linear equations. What's the objective there? In a general sense. Does anybody have a good idea what we're actually doing? Yeah, Exactly, we're finding those unknown variables. If we have this set of equations, we are literally trying to find those values of your unknown variables such that each of those equations hold true. So we're trying to solve for that same value of, like, say, x, y, or z in each of those equations. Now, is that always going to be possible? No. You might have an inconsistent system, which means there's no possible answer where if you find a value for x, y, and z, that it's going to be true for each of those equations. So you could have an inconsistent where there is no solution to your system. Which brings me to my next question, folks. What are the 3 possible outcomes for a linear system? This is the basic tenet of everything that we're going to do with linear systems. How many possible outcomes are there? Oh, we got it. We've got one solution, no solution, or infinitely many solutions. Good job. So that is something I want you to make sure you burn into your brain. If we are dealing with linear systems that are full of linear equations, all of our unknowns are to the first power, that means we only have 3 choices. We either got no solutions, where you have an inconsistent system, right? So that'll be another way of saying no solution. So no solution or inconsistent, or it could be a consistent system, which means it does have a solution. And so you either have one or infinitely many. There are no other choices. So if you get something else, something has happened. Anybody have an idea of why you can't have 2 solutions? Why does it have to be one or infinitely many? Why would 2 not make sense? Why would something other than 1 or infinite not make sense? Yes, they are lines. If you're dealing in straight linear lines, they can only intersect at one point. If they're intersecting at multiple points, oh, we no longer have a straight line, do we? We have some other equation. So linear equation, we're going to either, you can only have that one solution or infinitely many. Okay, so good job there. All right, so we're going to be looking at our next problem, number 5. So we have a good idea here of a system of linear equations and unknowns x1, x2, x3. So here we have, it says, find a system of linear equations that corresponds to the given augmented matrix. So here in number 5a, they've given us an augmented matrix. So that was one of the first key words that you needed to learn in that section 1.1 is an augmented matrix. Who wants to throw out there, why is it called an augmented matrix? What is so special about that? And they started playing around with it 200 to 100 BC in China, long time ago. What does it mean to be an augmented matrix? So we're going to want to know a lot of properties about the matrices that we're dealing with, because matrices are so cool. I hope you fall in love with them just like I have. Ooh, good job, Jose, because it includes the B, what comes after the equal sign. So it includes your constants. All right, your B's on the other side of the equation. All right, so that means, what would we say about this augmented matrix? What kind of system is this representing? How many equations do we have there with this particular? Yeah, we got 3 linear equations. Good job. And how many variables or unknowns do we have in this instance? If this is our augmented matrix, what can we look at that? Oh, yeah, we only have 2. We only have 2 unknowns. So our B's are going to be 0, 0, and 1. So they're written here on the right-hand side. The other thing I want to make sure that you notice is that you'll see that this matrix has brackets. So that's how we represent a matrix. You'll notice other types of line later, but make sure you realize brackets in this form denote a matrix. Okay, so here is going to be our augmented matrix. Let's go ahead and we're going to see what kind of linear equations do those equal. Let's see. So we've got here we've got in this one, here are our three equations that this augmented matrix refers to. So if you see this top row, that's going to be our first equation. So we have 2x1, and then you'll notice this has a 0. Now, if you want to, you could add plus 0x2 equals 0. So a lot of times that's helpful, even if you fill in the ones that have a 0 coefficient, because then it kind of helps you keep things kind of orderly and make sure you haven't forgotten anything. But in this case, they've decided just to leave a gap. You're free to also use different letters if you want for your unknowns. Like I said, they have used all X's with the subscripts. If you notice there's 3 unknowns, you could use X, Y, Z. There's 4, maybe add a W on there. So whatever is like easiest for you. A lot of times people like to just use the subscripts though. But here's our second row here in our matrix. That's going to correspond to our second equation. So we have 3x1. You'll notice this was a -4 in the matrix. So we have minus 4x2, and that's set equal to 0. Then you'll notice in this third row, that's our third equation, you'll notice we don't have an x1, or if you wanted to fill in 0x1 plus 1x2. The other thing that I also do is I also put in the coefficients, even if they're ones, sometimes to help me if I need to go back and forth between equations and matrices. So whatever you want to do, you could leave that as just x2. You could use 1x2. Either way is going to be fine. So that's going to be how you're going to represent this particular augmented matrix. These are your equations. Now, hint, hint, on an exam, you're going to want to be able to flip it back and forth, right? So if I gave you a set of equations, hint, hint, you would want to know, okay, well, what augmented matrix does that correspond to? So you would want to look at that keyword, augmented matrix. You'd realize, oh, I got to include my constants on the other side of the equal sign. So I got to make sure that those are included in my matrix. We won't always be using augmented matrices, so really make sure that you write down as part of your notes, this is an augmented matrix. All right, so we're going to go ahead and look at B really quick. So let's look at B. Here, what do we have this time? How many equations do we have? How many unknowns do we have? All right, we got 3 equations. Yes, 3 unknowns. Awesome. So this time, not quite so many zeros. So we'll check out and see what these equations are. So here we've got 3x1. They've got a gap here for the x2, and then they have minus 2x3. All that's going to equal 5. Ooh, this second row of the matrix, it literally has all of them. So we've got 7x1 plus x2 plus 4x3 equals -3. And then here is our third equation. They have a gap here for the x1. And then they went into their other unknowns. All right, so those are going to be your 3 equations, this time in 3 unknowns. Okay, so hopefully you guys have, Henny, you want to stop there? Does anybody have any question about this pattern? So you're going to want to know how a matrix can represent your equations. And then like the whole point of using these matrices, and because I love them so much, is it's going to make it so much easier for us to go ahead and solve for these linear systems when we use matrices. So it's a really, really cool technique. And you'll see how matrices are involved in so many different applications and engineering. But they're a really cool way to represent information easily and be able to manipulate how we need to solve for these systems. So next problem, so we did 1, we did 5. Let's go ahead and we'll jump down to 7. Okay, so like I said, remember, now we get the equations. So now we got to go ahead and find an augmented matrix. So if we're to look at this, oh boy, what can anybody think of really quickly? What would our matrix be? So this is going to be an augmented matrix for these 3 equations. So who can yell out what our matrix is really quickly on that one? Yeah, we've only got 3 rows. We've got 3 rows, 2 columns. So this one's a pretty darn easy one, right? So nothing too sophisticated there. I mean, we can solve this all probably in our head very quickly. So we wouldn't even really need a matrix for this, but you know, if we're gonna make one, here's our 3x2 matrix, and it's simply put in right here. Okay, so let's look at B. Oh boy. So that one's gonna be 2 equations. So we're gonna have 2 rows. How many columns are we gonna have? From part B, yeah, we're gonna have 4 there. So we have 4 columns. Don't forget we have all of our unknowns. Then we have our constant on the other side. So here would be our 2 rows, 4 column matrix. All right. Ooh, then we've got C. Ooh, what do we think our dimensions for that one's gonna be? So hopefully you'll be able to glance at these. Yeah, we got a 3x6, folks. So also don't forget when you see some gaps in here in these equations, we're going to put in zeros into our matrix, right? So since this first equation doesn't have an x1 unknown, we're putting a 0 in that spot. So when you make your matrix, please make sure you represent that spot with a 0. You know, when you're writing the equations, maybe you leave it out. So see how we don't have those terms in the equations, but when you represent it as the matrix, you got to make sure to put those zeros in the correct spots for those missing unknown variable terms. So please make sure you do note that. We have to represent them in the matrix. That's going to be really important, or our solutions are not going to come out correctly. So this would be the augmented matrix for part C. Okay, so any questions thus far? So not too bad, right? We're moving along. So let me see if I get any questions over here. Looks like you guys all know what you're doing. All right, our next problem then, we went ahead and looked at 7. All right, let's go ahead and we're going to go rocking down to 9. Okay, what do you think we're going to do for number 9? It says in each part, determine whether the given 3-tuple is a solution of the linear system. So here's our linear system. Who can tell me why in the world are they saying a 3-tuple? What in the world does that mean? Oh my goodness. What are they talking about with a 3-tuple? Yeah, we got a yeah, we're going to be representing our solution. So this all A through E would be potential solutions. They're represented as a coordinates for that potential intersection point if it is a solution. And so there's 3 coordinates here. So we got a 3-tuple. Depending on how many unknowns you have, you would have an n-tuple. So if you had things in n unknowns. So good job there. Yeah, so we got 3 unknowns that we would need to solve for here. So if you were presented with a problem like this and you didn't know anything else and you didn't know what to do with your matrices yet, how would you go ahead and solve this system? What might your train of thought be if you were given all these possible solutions? What might you do? Anybody have any ideas? Yeah, Cody, yep. Keep plugging in the numbers and checking them until we see which one makes all 3 of these equations true. So that's a really, really good point that Cody has here. Or if you feel like you already know what to do with a matrix, you could go ahead and solve using matrix row operations. You could do substitution. That could be cool too. So for here though, you want to make sure that whatever it is that you've plugged in, you want to make sure that this does in fact make all 3 of these equations true, because that's the whole point of solving this system. Whatever your solution is, it has to make all 3 of these equations true. Otherwise, it's not a solution to this system. So that's the whole point. Got to make each of those true. Now, like I said before, maybe none of them do. Maybe your system doesn't have a solution. So that is possible too. All right, so yeah, so for this one, you just plug in numbers until you got the right one if you didn't know anything else. Same thing with number 10. So I'll let you play around with those on your own. You can plug in all those numbers. Ooh, this one I highly recommend that you practice it because it's got some nasty fractions in there. And I have to say, some of our matrices are messy. So maybe just go ahead and do a little practice on some fractions. So 10 is not a bad one to go ahead and do. All right, so let's go ahead though and let's look at number 11. Okay, so number 11 we have for this part A, we have two equations. We've got two unknowns. They decided to use X and Y. So it says in each part, solve the linear system. So that means we got to solve for X and Y so that both of these equations are true, or figure out that, yeah, it's an inconsistent system, not going to happen. Okay, so they're going to say, it says, if possible, use the result to determine whether the lines represented by the equations in the system have 0, 1, or infinitely many points of intersection. Ooh, so they're asking us, what's happening with these systems? Do we have 0, 1, or infinitely many points of intersection? Okay, so here's the deal. If you went ahead and you reviewed your section 1.1, if you have infinitely many, then we're going to have to describe the solution as parametric equations. Ooh, boy. So we have to have a way to describe if there's infinitely many points of intersection. So who can give me an example? What would that mean if, let's just say, these two lines had infinitely many points of intersection? What would be going on with those lines? How would that be possible? Yeah. All right, so you'd have those concurrent lines right there on top of them. So that'd be a really, so I really encourage you to look in your chapter. They had some great images with, it is figure 1.1.1. So that kind of shows you what the difference is if you have no lines that intersect and if you have infinitely many, or you just have one point of intersection. So if you have two lines that have infinitely many, we call them coincident lines. All right, so we're going to go ahead and we're going to try some of these problems together. We're going to look at 11. So we're going to go through this because I want to make sure that you know what it means to find parametric equations and what that means. So I'm going to switch over to my iPad and we're going to go ahead and look at those. So give me 1 second here. All right. And all right. So you should be able to see my screen, hopefully at this point. And there we go. I will go ahead and let's see, make this a little bit bigger. Big as I can make it. Okay. So we are looking at our problem 11. So make sure if you hopefully you guys have been able to locate your books. And we are looking at problem 11. So if you see my screen, I'm going to go ahead. We're going to be looking at, this is chapter, let me just switch color here. Chapter 1, and I like to call them sections. And this one is 1.1. So we've got problem 11. All right, so we've got part A. which we have 3x minus 2y equals 4, and we have 6x minus 4y equals 9. All right. So does anybody have any idea of what kind of first step we might take to go ahead and solve for this system? Before we even use matrices, before we even get into that, if you were faced with these two equations, what might be your initial instincts? Yeah, so Cody says multiply the top equation by -2 to cancel out the x. Okay. So, all right, so if we do 2 times the first equation and we add it to the second, we would end up getting, what, 3x minus 2y equals 4. What would happen to that second equation then? If we did this first equation times -2 and then added it to the bottom, what would we get for the bottom one? Anybody have any ideas? Ooh, they would do what? What would we end up getting? Be something kind of a little strange, huh? Anybody have some numbers they want to throw out there? So if I did -2 times the first equation, added it to the second, ooh, I'd have what? 3 times -2 would be -6. 6x plus 6x, I'd end up with 0x. Then I'd have -2y times -2. Ooh, that'd be 4y plus 4y. Oh my gosh, I'd get a 0y. And then I'd have 4 times -2. I'd add it to 9. What the heck? So what do you think? What does this mean? This is not a situation we want. Ooh, yes, this means there's no solutions. You can't have 0 equal 1. So in this case, this particular system has no solutions. What's the other name for that? If we have no solutions or 0 solutions, this would mean that we have an inconsistent system. Boo, we don't like that. All right, we want to get to one that has some consistency here. All right, so let's check out our number B. Now we have 2x minus 4y equals 1. Then we have 4x minus 8y equals 2. Oh my goodness, without even doing anything. What do you think? Anybody have any thoughts about this? Oh my goodness, good call. So Jose says one is multiple of the other. Oh my gosh. So that should tell you. All right, so if we did the same thing over again, and we went ahead and did -2 times the first equation, added it to the second, we'd end up with 2x minus 4y equals 1. And then we'd have 0x plus 0y equals 0. Oh my gosh. So we have in this case, we saw here immediately before we're doing any math, these were multiples of one another. This should lead you to the conclusion that there are infinitely many solutions. That second equation doesn't matter what you put in for x or y. It also reveals no extra information. So that whole second equation, not even really even needed. All right, so we are left with, then we have 2x minus 4y equals 1. Okay, so how would we go ahead and write this as parametric equations? So what we're going to want to do is we would go ahead and solve for our x variable. So I think if you can see that we have then 2x equals 4y plus 1, then what are we going to get? Then we're going to go ahead and divide by 2. So we're going to get x equals what? Anybody want to throw it out there? 2y plus, what else we got? Well, hopefully you got 1/2. All right, so here's what you do. This is what we're left with. We're left with one of our variables expressed in terms of the other. So we are going to then use what we call parametric equations to describe a general solution to this system, which has infinitely many solutions, but we're going to basically provide a way to represent all possible solutions. So what we're going to do is we're going to assign y a parameter t. Okay? And then we're going to express our other variable in terms of that parameter that we've designated for y. So our x is going to equal 2t plus 1/2. So then this is a way that we would represent all possible solutions. And then that means we can fill in anything we want for that parameter t, and that would be what our y would equal. And then we'd go ahead and solve for our x in terms of that t parameter that we chose, and we'd have our value for x in that particular situation. And so these are all good terms to know. So you want to know what it means to describe your general solution in terms of parametric equations. We are going to have to assign our variable, one of our variables, a parameter, and then we're going to be able to express our other variable in terms of that parameter as well. So here is our general solution for this particular system. All right. So t is going to be any arbitrary real number. So we are going to be dealing in real numbers for this particular textbook. Okay, so as you might have guessed, we have one more part to look at, and that is going to be c. So we have x minus 2y equals 0 for our part c. And then we have x minus 4y equals 8. Okay. Woo. All right. So what do we think? What might we do again? So just hint, hint, this is kind of interesting. If we look back at our work, we had for part A, we had an inconsistent system. Part B, we had infinitely many solutions. Part C, let's see what happens for this one. All right, so we're probably going to go ahead and use that same strategy. Yeah, we're going to go ahead and multiply that top by -1. And we're going to go ahead and add it to our second equation. So we'd end up with x minus 2y equals 0. So we'd knock out that first x, and then we'd end up with 2y equals 8. All right, so those are going to be our two equations that we're left with. So if you notice here, we're not going to even worry about this term. So we have here -2y equals 8. I think we can easily see that y equals -4. So what do you think we're going to go ahead and do then? What would be an easy thing to just go ahead and do? Yeah, you're going to go ahead and plug in. Now that I know that y equals -4, I'm going to go ahead and plop it into that first equation. Anybody want to tell me what x equals? You can do that in their heads. Ooh, what do we get for x? If we plug in -4, all right, good job. We get, all right, looks like Joshua and Jose with a -8. All right, perfecto. Okay, so for that one, easy enough. So for this particular system, it was consistent because yes, there is a solution and we had one solution. And that means what? If we had just one solution, what does that mean for our lines? Good job. We have one intersection point. All right, so that means they're going to do their little thing and they're going to intersect at that one point. Now let's just go up really quickly to part B. Since that one was a parametric equation, it was a general solution. We had infinitely many solutions. Please realize it still means it's a consistent system because there are solutions. But what that would mean is that since there's infinitely many, that means those two lines are going to be coincidental. So they're going to be right smack on top of another. Then for our part A, which had no solutions and was inconsistent, means these two lines are hanging out in space. They're parallel to one another. They won't intersect at any point in time. So those are going to be what those look like. Okay, so let's go ahead. All right, so those are the different main points of your section 1.1. Make sure that you know what an augmented matrix is. Please make sure that you know what it means to be a linear system. What are your possible outcomes? Also want to make sure that you know what it means to use parameters and to create a general solution to your linear system. All right, so now we're going to go ahead into chapter 1. This is now going to be section 1.2. Don't you worry, you're going to get a break in a little bit. But we're going to want to get on to some other concepts here. Okay, so let me go ahead and switch over again. And we'll take a look at our textbook really quickly. So hopefully you have all found your textbook in the Canvas course. And if you have wanted extra resources, you can certainly get the ebook if you feel like buying it, but you should be able to have everything that you need with the PDF that I gave you in Canvas. All right, so here we go. Let's go ahead and see what we got next going on. All right, so here, if we go ahead and we'll see how chapter 1 and see how it has all these different sections in chapter 1. We have a lot of sections to get through for that first exam. So now we're moving on to section 1.2, Gaussian elimination. All right, here we go. All right, so Gaussian elimination. Who in the world are Gauss and Jordan? Who can tell me? Why do we care about Gauss and Jordan? Because we want to know about both of them. But it's really cool to know your history about your different mathematicians. But Gauss and Jordan had some pretty significant contributions. Yeah, we're going to be trying to manipulate our matrices. So what Gauss and Jordan had to say was really, really important because they are going to tell us how to go ahead and reduce our matrices to help us solve our different linear systems. So those are some cool dudes. So Gauss is when you're going to go ahead and use elementary operations to go ahead and go down your matrix and conduct some elementary row operations on that matrix. And then you're going to get to the bottom of your matrix. And then once you go back up and you go ahead and use elementary row operations on the way back up, then you've gone ahead and completed your second elimination with Jordan elimination. So you've gone both down and back up the matrix to get to your reduced row echelon form of the matrix. Okay, so here's the whole point of this. We have these ways to manipulate a matrix. And we want to do that because a matrix is going to be a really super useful way to go ahead and find the solution to our system of linear equations. So what we're doing is we're using these techniques. We're going to represent our equations by a matrix. Then we're going to manipulate that matrix and we're going to put it into reduced row echelon form so that we can go ahead and get the solution to our equations. So if we look at this matrix, this is called reduced row echelon form. And it has a lot of different properties. Okay, so you're going to want to make sure that you have memorized those 4 different properties to become a reduced row echelon form of the matrix. Okay, so upon these manipulations, we're doing these together. But if you do these elementary row operations, you'll get to a matrix that might look similar to this. And so here are different properties for this to be called a reduced row echelon form of the matrix. You'll also see me abbreviate it RRE, so don't be confused if you see that. So here it says, number 1, if a row does not consist entirely of zeros, then the first non-zero number in the row is a 1. So this is a leading 1. Look at that top 1 there. Okay, it's a doesn't consist entirely of zeros. That first non-zero number is a 1. Boom, it's a leading 1. Number 2, if there are any rows that consist entirely of zeros and they are grouped together at the bottom of the matrix. Okay, well this one didn't have a row of all zeros, but if it did, they'd be at the bottom. Then 3, if any 2 successive rows that do not consist entirely of zeros, the leading 1 in the lower row occurs farther to the right than the leading 1 in the higher row. So we can see that. So see how this one has a leading 1 all the way over to the left? The next one is now further over to the right. And then look at this third row. This next leading one is even further over to the right. So that's perfect. All right, and then number 4, each column that contains a leading 1 has zeros everywhere else in that column. Okay, boom. All right, well, let's check out this leading 1. All right, there's zeros below. We've got this one here. We got zeros above and below. Good deal. There's this third leading 1, all zeros above. Now, what you'll notice here is you do have a column that does have numbers, but guess what? This this leading 1 for this bottom row is here. So it's okay to have these numbers along this 4th column because we could only have this one leading 1 in this row. So these numbers over here to the right are safe. They still meet all the qualifications for a reduced row echelon form. Okay. So the whole point is we're trying to do this to our matrices to get a solution for our system. That's why we even want to do this in the first place. Okay, so let's get to some problems to kind of demonstrate some of this. So section 2, so here's our fun mathematicians. So here's Gauss, and then here's Jordan. So they're the ones that came up with all these elementary row operations that you can do on a matrix. And we have to make sure that we remember what those elementary row operations are, because they'll let us do some. So that's the other thing that they point out in this particular section, is what are you allowed to do with that matrix? Okay, so let's go ahead and we'll get to our problems. Okay, ooh, all the way down. So like I said, I hope that you reviewed your content videos because I'm counting on you to know some of your terms so that we can spend majority of our time working problems. Okay, Here is our first problem. Okay, so it says determine whether the matrix is in row echelon form, reduced row echelon form, both or neither. So here's your first trivia question to see if you all did your content videos. What is the difference between a row echelon form and a reduced row echelon form? Anybody know? What is that difference? Who knows? What is that big difference between a row echelon form of a matrix or a reduced row echelon? There's a key thing that's different. Because they're going to be close. They're going to be a lot of times close in form, but there's a big key difference. I don't see it quite yet in your answers. So keep looking, keep guessing. What? So let's see. We have reduced contains zeros after the leading one for each row. Well, think of a good way to say that. If you're in reduced row echelon form and you've established those leading ones. There you go for Milton. Yes, if you have reduced row echelon form, you have zeros above and below those leading ones in that column. So that is going to be your important distinction. All right. Okay, so your row echelon form does not require zeros both above and below that leading one. It only requires zeros below. So, all right, so let's get on to some questions here. All right, let's look at A. What do we think? Is it reduced row echelon form, both, or neither? What do we think? Yay, it's both. Why would it be both? Well, if you're in reduced row echelon form, then you're automatically in row echelon form, right? So that one, dun 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 dun, both, woohoo! All right, what do we think about B? Ooh, is that going to be reduced row echelon, just row echelon, or both? Yeah, it hits all four, and so 3, both. Awesome job. Boom, both. Ooh, look at C. What do we think about C? This one's kind of interesting. All right, I'm seeing both from people. So here, this is interesting. So this one's a little bit different, but it still fits all the definitions for reduced row echelon form and therefore also being in row echelon form. The first leading one didn't happen in this leftmost spot, but that's okay because each subsequent leading one was still further over to the right. So it still met that definition. And then you had your row of zeros at the bottom. So just remember your first leading one doesn't always have to be in this leftmost spot as long as it's the furthest one to the left out of all of them. Okay, so, all right, so we've got C was both. All right, let's look at D. What do we think about D? D is interesting too. So yeah, so we got both as well. So here's a leading one, got a 0 below it. Here's our next leading one. It's further over to the right. It's got a 0 above it. So it's fit those definitions. it's okay that we have numbers here, because how many pivot columns can we have for this particular matrix? Yeah, we only get to have 2 pivot columns because there's only 2 rows of our matrix. So there's no way to have any other leading ones if you only have the 2 rows. So we're limited to 2 pivot columns, and then we also have 2 pivot rows. Okay, so this one also would be both. So don't be tricked out by having these other normal numbers over here. You have to have zeros above and below leading ones to be reduced row echelon form. If you're able to get all the way to reduced row echelon form, then you already inherently have row echelon form as well. Okay, so then let's look at number E. What do we think about E? So a lot of these are worth carefully looking at. Okay, we got an answer for both. All right. This is another cool one to look at because it might not look like how you would expect. So let's go through it. We got a leading 1, all zeros below it. Oh, well, interesting. Our leading 1 skipped a column, but that's okay because we're still fulfilling the definition. So here's our next leading 1. It's further over to the right. It has zeros above and below. That's cool. So we're doing good for a reduced row echelon form. Oop, we skipped another column. That's okay. Our next leading 1 is in the row below, but it's all the way over a little bit more, but it's still further to the right. Still, there's zeros above and below it. Good call. And they put all the row of zeros to the bottom. So we are looking good for both. Woohoo! All right, let's look at F. What the heck do we think about F? Ooh, interesting. We got some. People are thinking, is it neither? Is it both? What? All right. Well, guess what, folks? If you want to make sure you look at that definition closely, because it says if you have non-zero numbers, then you need to have a leading 1. But guess what? We have zeros here. So guess what? It's both. So there's no requirement that you have 1 unless you have non-zero entries. But here we have all 0 entries, so it still fulfills all the definitions. So it's a little bit of a trick. So F would be both. There are no leading numbers or any other numbers at all. Okay. All right, so then our last one. So here, just to show you with the definition here, let's see. We go up to our, don't forget. So we go all the way back up to our definition here. Dun, 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 dun. Sorry while I scan. All right, here it's got to have these properties. It says if a row does not consist entirely of zeros and the first non-zero number in the row is a 1. Well, we're okay with that matrix of all zeros because this one says if a row does not consist entirely of zeros, then that first non-zero number has to be a 1. Well, in this case, we had all zeros. So we still met all of our rules. Dun, dun, dun. So that's another important point for this course. You're going to have to make sure that you read all of your definitions super carefully. All right, so the other thing too, this has some other very important points. Every matrix will have a unique reduced row echelon form, but you might have a lot of different row echelon forms. Those are not going to be unique because you might have gotten to your unique reduced row echelon form in different ways. So you'll get there through different row echelon forms, depending on what set of elementary row operations you decided to do in what order. But You do have a unique reduced row echelon form for each matrix, so that's good to know. Any of your rows or columns that have a leading one, those are going to be your pivot positions. So we saw that. Okay, so we looked at problem 1. Okay, we're going to look at 3 really quickly. Okay. Oh, sorry. We were supposed to look at G really quickly. G, what do we think about that one? Oops, sorry. There it is. G. What is that one? Yeah, that's only row echelon form. Here we've got a leading one, looking good. The next leading one we see is further over to the right, looking good. But guess what? This -7, this tells us that it's only in row echelon form. We'd have to turn this into a 0 before it becomes reduced row echelon form. So this one is only RE. Okay, so that kind of shows you some different ones. So I encourage you to do 2 on your own and see if you can figure out all of these, test yourself. Because hint, on the exam, I might ask you, is it reduced row echelon form? Is it row echelon form? Or is it both? Or neither? Okay, so let's go ahead. We'll jump to our next problem, number 5. That's got some good concepts here. Oh my goodness. So number 5, Gaussian elimination. So here's the thing. We're doing all these elementary row operations in order to solve the system. So this particular question, though, it's telling us to solve the system by Gaussian elimination. So what should that mean to us if we just do Gaussian elimination, if we just go down the matrix with our elementary row operations? What do you think we're going to end up with if we're just looking at Gaussian elimination? Yeah, good job. We're going to have some sort of back substitution because we're only going down the matrix. If you just do Gaussian elimination, what kind of matrix do you end up with? Looks like, I think you answered in the same question, I guess, yeah, so reduce echelon form. So you'll just have REF. So good. So here's why they came up with all these elementary row operations. They want for you to be able to solve this system. But they're giving you a lot of hints by saying solve the system by Gaussian elimination. So that means you only go down the matrix, you just get to row echelon form. Usually you're going to have probably some sort of back substitution, which then should tell you what possibly about your system. Anybody have any ideas? What do we think? Anybody? What should that tell us? They're giving us some serious clues with this system. Yeah, so if you are, they say they're going to solve the system by Gaussian elimination. That means we're going to go down our matrix with elementary row operations. It means we're going to have some sort of row echelon form of our matrix. And so we'll probably be using back substitution. So what do we have a good guess as to what might be happening with this system then? What might be? Yeah, so we're going to be when we think about what kind of solutions will we end up with here. All right, so let's go ahead and we're going to try this together and then we'll go to break because I know y'all are probably needing it by now, right? So we're going to get us to our break. Okay, so we're going to be looking at problem 5, okay? So let me go ahead and I'll switch over. Bum, 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 bum. All right. And okay. get us back. Okay, so we're on chapter 1, section 1.2. We're going to look at problem 5. I encourage you to make sure you can locate it in your book. And here we go. So problem 5, we have x1 plus x2 plus 2 x3 equals 8. We also have negative x1 minus 2x2 plus 3x3 equals 1. And then our third equation here, we have 3x1 minus 7x2 plus 4x3 equals 10. Okay, so we're going to want to go ahead and represent this with an augmented matrix. So we know what that is. All right. So we're going to go ahead and put that in. Look at our equations there. We're going to have 1, 1, 2, 8. Then we'd have -1, -2, 3, 1. And then we've got 3, -7, 4, 10. I'm going to go ahead and put my brackets to show that it's a matrix. This first column is going to be our x1 coefficients. That second column will be our x2 coefficients. We have our x3 coefficients. And then these are going to be our b constants on the other side of the equal sign. So that's our augmented matrix. Now, hopefully from your content videos, you're very familiar with the different elementary row operations. So we're going to be using elementary row operations. And the whole point of it is to use those so that we use Gaussian elimination. And we want to simplify our matrix going down the matrix. We're going to go down the matrix to simplify our system. Okay, so that's all we're doing. We're just going down the matrix. So that means that we're going to go to our row echelon form. All right. So who can tell me what are those 3 elementary row operations that we're allowed to do? What are these fantastic row operations? There's only 3 of them, and they're super cool. So what are we allowed to do? Does anybody know their elementary operations? All right, so yes, you can interchange rows. You can multiply a whole row by a non-zero constant. And you can also multiply a row by a non-zero constant and add it to another one. So those are our 3 operations. And the whole point is to simplify this matrix so that we can find our solution. And we're trying to get it into row echelon form of the matrix. So into REF. Okay, so let's look at this matrix that we have here. Well, we're looking super good because we already have a nice little leading 1 in that top left spot. So I think we're going to just leave that alone. Ooh, does anybody notice anything cool that we can do for our first elementary row operation that kind of makes use of our 1 there? Well, hopefully you notice. Yeah, we could add row 1 to row 2. So technically, if you want to follow the rules officially, we are multiplying our first row. So 1x times the first row added to second. Okay, so we're going to go ahead and add 1x the first row to our second. So that means we should get 1, 1, 2, 8. Anybody want to shout out what our new elementary row operation is for that second row? What will we get? Who knows what our next row of our matrix should be? See if anybody who can type the fastest. All right, good job, Maximilian, for the win. We've got 0, we've got -1, 5, and 9. So that came from adding 1 times the first row added to the second. All right, so now we have for our third row 3, -7, 4, 10. All right, well, what do we notice? We have to get rid of this 3. We need to have all zeros below our leading ones. Otherwise, that's not a true leading one, right? So we have to get rid of that 3 there. So what do we think? We're going to make use of that first row. So we are going to add -3 times the first row to the third row. And why did I pick -3 times that first row? Oh my goodness. Why did we pick that? Well, if I do -3 times that 1 and then add it to the 3, yeah, I'm canceling out that 3. I'm making it become a 0. All right, so I'm going to go ahead and fill in my new matrix. So we get 0, -1, 5, 9. Okay, so that's third row. What am I doing? I'm doing -3 times all of these numbers. So -3 times 1 plus 3, that becomes a 0. Then I do -3 times 1 plus -7. Ooh, that becomes a -10. Then we do -3 times 2 plus that 4. So what do we got? We got -6 plus 4. We get -2. Then we've got -3 times 8 plus 10. So that's -24 plus 10. We get -14. So there, we're getting there. We're getting down there. So obviously, once you see this pattern, I know you all will be able to blow through this super fast, but it's just showing you step by step what's going to happen. Okay, so we've got our first leading one. Woohoo! All right, so we have to have our next leading one further over to the right. Well, ooh, this is looking like a good candidate, but we got to get rid of that negative sign, right? So we're allowed to multiply our rows by a non-zero constant, right? So we're going to go ahead and multiply that second row times -1, right? So we're going to get, oops, sorry. Getting ahead of myself. Got 1, 1, 2, 8. Then we got 0, 1, -5, -9. So I just went through and did that whole second row, multiplied it by -1. Okay, and then we still have our third row left in there, -10, -2, -14. Okay, so it's looking pretty. We got this leading one here. We got our next one here. But what's the problem? What do we got to do next? Why is this one not fully a negative or next leading one? Well, we got to get rid of this pesky -10, right? We got to get a 0 below it. Yeah, we got to make it a true leading one, so there's zeros below. Okay, so we're going to go ahead and do 10 times the second row added to third. So yeah, so if I did 10 times that leading one, added it to the third row below, I'd be getting rid of that -10. Ooh, so let's go ahead and try it. We should get 1, 1, 2, 8. We should get 0, 1, -5, -9. Okay, so here we go. We're going to do 10 times the second row and add it to the third row. Okay, so we've got, so don't forget, we're going to go 10 times all of these numbers across that second row and add it to our third row. All right, so 10 times 0 plus 0 is 0. 10 times 1 plus negative 10 is 0. Yoo-hoo! We got our next leading one. All right, we got 10 times negative 5. Oh my gosh, plus negative 2. Okay, so now we have a negative 52. Ooh, boy. Okay, then we do 10 times negative 9 plus negative 14. Who wants to give me what that big number is? Who's got that one? What? Oh, good job. Negative 104. Awesome. Okay. Oh, we're almost done, folks. See how the pattern we've emerging here? So we've got a leading one here, a leading one here. Oh, ooh, we need to turn this into our next leading one. Anybody have any good ideas? What are we going to do? Who wants to guess what the heck we're doing on that one? Do. Yes, I really like that. Yeah, so you're going to divide that last row by negative 52. So we're going to divide by negative 52. That way we get 0, 0. Now we get a 1 here. What's a negative 104 divided by negative 52? Anybody know? So yeah, the better way to describe that, because really you're only allowed to multiply, it would be 1 over negative 52 is technically what you're doing, because you're multiplying each row by a non-zero constant. So good point. So that last number here is negative 104 times 1 over negative 52 would be 2 here. Now, I'd like to go back to a question that was really, really good. Let's see. Hold on. Who asked it? Somebody asked something about why can't you use row number 1? Why did it have to be row number 2? That's a great question, because if we did 10 times that first row, you'd end up with a number back in this, you'd end up with a number here instead of a 0, and then you'd be adding a number into this space. So this would then become a 10. So if you did 10 times that first row, added it to the third, you'd now have a 10 in this spot. And we don't want that, because we wanted to keep that a 0 so that we have a true leading 1 up here at the top left. So we have to be very careful about what rows we pick and what we're trying to accomplish. You don't want to use any row where you all of a sudden, get rid of that nice pretty 0 that you have. So definitely want to make sure that you choose rows correctly. So that's why we were working a lot with that second row, because if we multiplied something above it, we still kept our zeros in that first column. So great question there. So that is why we didn't do that. But now we have leading 1. Oops, sorry. What's going on here? It's erasing. So now we have a leading 1 here, a leading 1 here, and a leading 1 here. Now, this is row echelon form. Why is it not reduced row echelon form? Because we still have numbers above our leading 1s that are not zeros. So keep in mind, this is only row echelon form. Okay, so REF. So now we have this great little thing where we can do our back substitution, right? We can see that we have we have these really nice leading 1s that are just in nice 1 steps here. So what does this matrix mean now that we have this result? What do you think we can do now? Does anybody have any ideas there? So you'd want to look at this last third row. Yeah, so then we're going to go ahead and go back and put that in. So this was, don't forget, this was our X3 column here. So here we automatically can see from this leading one here at the bottom, this last row, we can see that X3 equals 2. So now we can plug it back into this second row. So what does that mean our second row is? Okay, well, our second row, we have no X1, we have an X2. All right. Minus 5x3 equals -9. But guess what? We know what x3 is now. So now we have, what are we going to put in there for x3? We're going to put in that 2. So we have x2. If we rewrite this, this is going to be what? What are we going to put in there? So this will be 5x3 minus 9. Who can tell me what x2 is? Looks like you guys already got the answers. All right, so our x2 is going to equal 1. All right, we only have 1 left. So what's our equation here for x1? So if we look back at the top row of our matrix, we've got x1 plus x2 plus 2x3 equals 8. Oh my goodness, we already know what all these things are though. We rearrange that and we say x1 equals -x2 minus 2x3 plus 8. All right, well, we know what x2 and x3 are. So who wants to tell me what x1 equals? Anybody know the answer for that one too? So this one we put in -1 minus 2 times 2 plus 8. That should hopefully help you out a little bit there. Let's see who can get that. Oh, looks like Keegan got it for the win. We get 3. All right, so here's our x1 equals 3, x2 equals 1, and x3 equals 2. Here is our solution by using Gaussian elimination. So we use Gaussian elimination to get to our row echelon form of the matrix, and then we could easily use back substitution. And we got to 1 unique solution. So that's cool there. All right, we'll leave it at that, folks. I know you need a break. So we're going to get that break. And I will see you back. Go ahead and put that in there. We will break until, was it 4:08 p.m. And I will see you back then. right, we are back. So we discovered that with that problem that we had, and we did Gaussian elimination, that we got a unique solution. The next problem that we're going to look at is problem 9 in your textbook. Now, the cool thing about that is it says in those exercises 9 through 12, solve the system by Gauss-Jordan elimination. And what that should tell you is now you go down the matrix. So down the matrix to get to your row echelon form with your elementary row operations. And then you're going to go back up the matrix with your elementary row operations so that you get to reduced row echelon form. So now that you have zeros both above and below your leading ones. So that's going to be a really, really important distinction. So when we just did Gauss elimination, we just got to our reduced echelon form and we used back substitution and all that great stuff. But now they want us to prove that we can go ahead and do Gauss-Jordan elimination. We get to our reduced row echelon form, and we should get the same answer because they're asking us to use the same matrix as in exercise 5. So we're going to go ahead and do that, and we're going to start with the step that we left off at in our previous matrix. So we left off at 1, 1, 2, 8, 0, 1, -5, -9, and then we had 0, 0, 1, 2. So don't forget this was our row echelon form, and we stopped here because we had our 3 lovely leading ones and we could do our back substitution to get our answer. But now they want us to keep going and use Gauss-Jordan elimination. So we're not done. We have not finished the new task because they're trying to show us the difference between these two forms, but also the fact that you can get to the same answer here. All right, so we're going to keep going, and now we're going to go back up the matrix. So now we have these leading ones, but now we need to make sure that we have zeros above our leading ones too. All right, so we're going to start in our third row here, and we got to get rid of that -5, and we got to get rid of that 2 above it. So we're going to go ahead and take a look at this third row here. So we're going to go ahead and we're going back up the matrix. So we're going to strategically use our elementary row operation where we're going to take 5 times the third row and we're going to add to our second row. And that's so we can get rid of this -5 here and turn it into a 0. So like I said, we're going back up that matrix. All right, so we're going to take 5 times the third row, add it to the second row. So we're going to go ahead and we'll get 1, 1, 2, 8 for our first row. Ooh, now we're going to start manipulating our second row here. So if we do 5 times the third row, so 5 times 0 plus 0 is 0. 5 times 0, plus 1 is going to be 1. Then we have 5 times 1 plus -5. Oh, yay, we got a 0 in that spot. Okay, now we do 5 times 2. Add it to the -9. Who can guess what we put in that spot? Well, hopefully you see that 10 plus -9 equals 1 there. So yay, we've gotten rid of that -5. Along the way, we've also changed that 9. So now our bottom row still is this. Ooh, it's shaping up. All right, well, we're looking at this leading 1. We still have this pesky 2 to get rid of. So you guessed it. What are we going to do? We've got to get rid of that 2. So we're going to do -2 times our third row. And hopefully you guessed right and you said, oh, I'm going to add it to the first row. Got to get rid of that 2. All right, so let's do it together. Okay, so we're doing -2 times that third row, adding it to our first row. Okay, so -2 times 0 plus 1 equals 1. All right, -2 times 0 plus 1 equals 1. Then we get -2 times 1 plus 2. Oh, we get our 0 there. Yay! Okay. Then we have -2 times 2. Ooh, what do we get? -4 plus 8. Ooh, this now changes this to a 4. Okay. All right, now let's see how we're looking. We're going to put in our other rows here. So we got 0, 1, 0, 1. We got 0, 0, 1, 2. Ooh, we're getting there. Okay, so now we only have one other leading 1 to worry about. All right, so here's our other leading 1. Now we got to get rid of this 1 above it. Okay. So let me go ahead and ask you all, which row are you going to choose now to get rid of that 1? What do you think we should choose? Well, the third row is not going to really help us out because anything we multiply by 0 is going to give us 0. All right, we got a suggestion in there. Awesome. We've got, okay, we're going to multiply row 2 by -1x. Okay, so -1 times our second row. And we're going to add to our first row. All right, so -1 times our second row added to the first. All right, so -1 times 0 plus 1 equals 1. Ooh, we got -1 times 1 plus 1. Ooh, yay, now we get that 0. All right, now we get -1 times 0 plus 0. Oh, we got a 0. All right, now we have -1 times 1 plus 4. Okay, this is now going to change that to a 3. All right. Now we're going to fill in the rest of our zeros. Or sorry, the rest of our rows. And look at this. So this one is in such a much prettier form. So here you can see the advantage of going all the way to reduced row echelon form. So don't forget, this one is now RREF. But this one it's so easy to see then our one-to-one correspondence here. So it's really easy to see that x1 equals 3 from our top row. Then our second row, we can easily see that x2 equals 1. And then from our third row, we can easily see that our x3 equals 2. And there's our unique solution. So when you use that, go all the way down your matrix, go all the way back up, you really see those one-to-one correlations there for your unique solution. The other thing too is you don't have to worry about doing that back substitution because you've already done that along the way. So we end up with that same solution of 3, 1, 2. And that was by doing it 2 different ways, but we ended up with the same result. So just wanted to show you all that. So benefits to doing it either way, depending on, you know, what you prefer. So you can certainly stop at just row echelon form and then go ahead and do a back substitution. Or you can continue with your matrix getting to reduced row echelon form and then being able to see easily your final answer. So I'll leave it up to you as to which you prefer, but just you want to make sure you know how to do both. All right. So we are going to be moving into our problems for chapter 1, section 1.3. Oh yeah. So in section 1.3, we are learning a lot about how, oh, I just realized I skipped a problem. My bad. All right, let's look at problem 13 really quickly because that's important. Sorry, before we move on, let's look at problem 13 super quickly. So problem 13 is 2x1 minus 3x2 plus 4x3 minus x4 equals 0. Next one is 7x1 plus x2 minus 8x3 plus 9x4 equals 0. And then our last line is 2x1 plus 8x2 plus x3 minus x4 equals 0. So the other part of this section talked about this type of linear system. So who can tell me what problem 13 represents? Yeah, exactly. You can immediately tell the unknowns without having to plug in. All right. So with the problem 13 that I have written down there, who can tell me from doing their concept videos or reading the chapter beforehand, what is this system known as and why? So what do we immediately notice about this system? So this will be a very important. All right, excellent job. This is a homogeneous system. So please make sure you know what that term means. So what does it mean, folks? If I say you have a homogeneous system, what the heck does that mean? Yeah, they're all set equal to 0. So all equations equal 0. And so this is a very interesting type of system. It's different than if you had numbers that were on the other side of the equal sign that were not 0. What's interesting about this system is if you have a homogeneous system, it will always be consistent. And what does consistent mean? Yes, it means that you will have as a solution. So this is a cool system. It will always be consistent. It will always have a solution. Now, because this is a linear system, when we say that it has a solution, we still have choices. Does it have one solution or infinitely many? But either way, you know that a homogeneous system is going to have a solution. If it has one solution, who can guess what that might be? Yeah, they all intersect at the origin. That would mean that x1 equals x2 equals x3 equals x4, and they would all equal 0. So you can always get a solution by plugging in 0 for your unknowns. You will always have that as a guarantee with a homogeneous system. You'll always have an intersection there at the origin. What you don't know is, do we have just that one solution, or will we have infinitely many? Well, they're asking you in this problem to, without doing any math, without doing any matrices, can you tell which one will it be? Will it just have one solution or infinitely many? So I think somebody had already kind of answered it. So definitely chime in again. But you should be able to see by inspection, by just your own 2 eyes, which one should it be? Because if you've gone through that section, done your flipped classroom where you've reviewed those sections, looked at your videos, what do you guys think? Do you think that that system will have one solution or infinitely many? One solution looks bizarre. Lot going on. Add 0, 0, 0, 0, 0. But so this is something that you'll want to take note of. All right, so it looks like I'm not sure if anybody's sure yet. So definitely review this section. But you will notice that for this system, there are more variables than equations. So we have x1, x2, x3, x4. So we have 4 variables and we have 3 equations. That should automatically tell you that if you're dealing with and this is only for homogeneous systems, if that's the case, then you have infinitely many solutions. So you already know something about this system. You know what you should get. That means that you will end up with parameters. It means you're going to end up with parametric equations. So if you see that you have more variables than you do equations, and it's a homogeneous system where they're all set equal to 0, then you know you have infinitely many solutions. And so if you get something else, you know that some math has gone awry along the way. Now, if you had a system where all of these were equal to constants, it also tells you something interesting. So if you have a non-homogeneous system, if you have more variables than equations, then you have narrowed it down to either it's inconsistent, where there's no solution, or there's infinitely many. You will not have a unique solution if you have more variables than equations. But since it's a non-homogeneous system where they're not all equal to 0, you don't know yet if it's inconsistent or if there's infinitely many. So you'll still have to kind of go through your matrix and figure that out. But it did eliminate one of the possibilities. You will not have a unique solution. And then with a homogeneous system, you can immediately look at it and know what's going to happen. All right, so those are really, really important properties. Okay, so now I feel comfortable in moving on to chapter 1. We are now going to be in section 1.3. Okay, so some really, really important things with this section 1.3 is that you really need to look at your matrices and understand what you can and can't do with them. And so one of the first things that you always want to look at is your matrix size. or what we call its dimensions. So when you're thinking about describing a matrix and you want to report its dimensions, you always report it as row by column. If you have a 3 by 5 matrix, that means you have 3 rows by 5 columns. So that's what that means. The other thing this is really important is this lets you know if you can add and subtract matrices or multiply them. You need to know the dimensions because you can only do certain things if they're the right size. So if you want to add or subtract matrices, hopefully you remember this from your review of those sections. If you want to add or subtract matrices, they have to be the same size. If you want to multiply matrices, you're going to have to figure out, can you do it? So they have that really cool tip where you're going to look at the inner and outer dimensions of your matrix. So it's really, really important that you look at that. So if you happen to have a matrix that is, say, a 3 by 5, and then you have another matrix that's a 5 by 3, well, you would look at the inner numbers here. So this would be the first one's columns compared to the next one's rows. And so these inner numbers here are both 5. So, yep, you can multiply. Yay! And your product will be a result of those outer numbers. So you'll get a product that is a 3 by 3. So you have to look at those. Now, this only works when order matters, right? So you can't just reverse things anytime you want. So this predicated on the fact that the 3 by 5 matrix came before the 5 by 3. Because if you reversed the order, you might not always be able to multiply things. For instance, if you had a 3 by 5 versus a 5 by 2, so if this was A and this was B, so that means you could multiply AB, but if you reverse the order and you did the 5 by 2, which is B, and you wanted to multiply it by A, 3 by 5, ooh, you look at those inner numbers and guess what? Nope. So if you were trying to multiply BA, boo, you wouldn't be able to do it. So like I said, huge deal is going to be order. So order matters with multiplication of matrices. All right, so let's go ahead and check out some before we leave here. We got a couple we get to look at before we leave here today. So let's do it. Okay, hold on. There we go. Get that to. All right. So let's see what we have for our problems. All right, so like I said, we are in chapter 1. We've got quite a few sections to do. We're on 1.3. So let's go ahead and look at some problems at the end of that section. Dun, 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 dun. So here's that cool rule I just showed you, right? Got to look at those inside numbers. And if you're talking about the dimension of a matrix, you always report rows by columns. So want to make sure you keep those definitely straight. Okay. So if we go to the end of our section here, let's look at these. Ooh, okay. So here's the matrix, A, B, C, D, E. All right, so we look at, okay, let's look at the product BA. So like I said, order matters. So if we looked at BA, can we do it? Can we make that product BA? No, boo. Because we reverse that order there, BA, we'd have a 4 by 5 times a 4 by 5. Those inner numbers would be a 5 and a 4. So no, can't do it. It would be called undefined product. Okay, let's look at our next one. Ooh, AB superscript T. Ooh, I like this question. So hopefully those of you who reviewed your sections, what the heck does that mean if we have this T superscript? So we've got B superscript T. What's that? Ooh, why do we care? Oh my goodness. So that'll be a vocab word you're going to want to know. What does that mean when you see B with a superscript T? Let's see who can find it in their books the fastest. All right, Milton. Yeah, you got it. Transpose. So what that's saying is that is the transpose of B. And who can tell me what a transpose is? Oh, good job, Joshua. Yeah, you're switching your rows to columns, so it flips them. All right, so B up here has 4 rows and 5 columns. That means the transpose is going to be the opposite. It's going to have 5 rows and 4 columns. All right, so let's look at that. All right, so we're going to take that transpose of B. Can we do ABT? Can we do it? Oh, heck yeah, we can. Because if we take the transpose of B, which would now have 5 rows and 4 columns, so it would be now a 5 by 4, that means that 5 would now match the inner 5 of A, and we'd be able to say, yay, yes, we can. So yes, it would be defined, and it would be a 4 by 4 matrix. All right, let's do another AC plus D. Oh, okay, so got to remember your order of operations from your regular algebra classes. So we're going to multiply AC first before we add it to D. So let's look at AC. Can we do it? Ooh, yes, we can. See the 5 here of A and the 5 here of C, they're in the inner. So we can multiply them. What would that product be if we multiplied A times C? Anybody know? So if we did our product AC first, oh, good job. Yeah, we have a 4 by 2. So we take those outer dimensions, 4 by 2. All right, so we're working with a 4 by 2 matrix. And now they're asking us, can we add D? Oh, look at that. D is a 4 by 2. Yes, we can, because it's the same size. So don't forget, if you're adding and subtracting, has to be the same size. If you're multiplying, you have to do that little dimension test. Okay, we'll do one more, and then you guys get out of here. All right. Oh, look at this. We're going to do E times AC. Don't forget your algebra. The parentheses are telling you what you need to look at first. So it's asking you for the product AC first. So can we do it? AC? Yes, we did. We determined we could. We determined that AC was a 4 by 2 product. Right? Okay, so now we have to find out EAC. So E is coming first. Although we did that quick product AC first to find out what it was, when we now have to multiply E times it, E comes first. So that means that E is 5 by 4. Our product for AC was a 4 by 2. So can we do EAC? Yes, we can. And we're going to get a 5 by 2. Oh gosh, you guys are good. Okay, yes, define. It's going to be a 5 by 2 matrix. So you can see how that goes. All right, folks, make sure that you look at 3, because, ooh, now you're going to have to, it's kind of the same thing. You have to figure out, can you do it or not? All right. This time they're asking you to go ahead and calculate it. You don't have to do that. We'll go ahead and go over the answers next time, but look at problems 2, 3, and 5. And we'll check your answers next time. But you're going to want to make sure that you know whether or not you can do it by those properties we talked about today. And we'll look more closely at multiplication of matrices next time, because you're going to want to make sure you know how to do that really, really well. So, okay, folks, we are going to make sure that we look at really quickly before we leave here. Please make sure that you don't forget that we have your team assignments due today. Let's go ahead and also look at your schedule. So always be looking at your schedule. If you miss a class, you'll know exactly what we went over. So as you notice today, you have your Decide Teams assignment due and you have your Honor Lock setup assignment due. So please make sure you finish those today. With that Decide Teams assignment, please make sure that you all individually submit. I want to make sure that everybody knows each other's team names. I want to make sure that you all have agreed to form a team. So everybody needs to turn in this Decide Teams assignment, not just one person, everybody in the class. Okay, so please make sure you find those and make sure you get those done tonight. They're not hard. Just gotta make sure you do it so you get your points. And I will be seeing you next Tuesday for more fun problems. This time we'll know your teams, so we'll now be able to have some friendly competitions. But you guys have done an awesome job participating today, so thank you very much. Let's see. So if people had problems with their side cameras, then they'll need to make sure that they send me a Canvas message to let me know what's going on. And I will answer them directly. But everybody should hopefully have their side camera by today, since you had last week to get it. So I don't anticipate that will affect too many people. But definitely make sure you get that in if you can. Otherwise, this Honor Lock setup assignment, it will be open until Friday with no late penalty. So if you can't get it done tonight, make sure you get it done before the Canvas submission window closes. So you always want to look at an assignment and see when the final window closes, in case you run into some problems. So you should be good. All right, so you're free to disperse. Please make sure you reach out to people and get those teams in. I look forward to seeing who you all decided to work with. All right. All right. Thank you all. And yep, go for it.
For the team assignment thing, I'm still waiting for a couple of partners. Is it still due today, or is it still due later this Friday?
If you need more time to figure it out, you can turn it in by Friday with no late penalty, but it will close on Friday. So we need to have the teams formed before next week, so that we know how to arrange you into teams for games and to do your team assignments coming up. So definitely try to get that done this week if you can't do it tonight. Does that sound good?
Yeah, and for the camera thing, it's also due this Friday as well?
It's officially due today, but you do have a grace period in case something has happened. But you have to get it in before the Canvas submission window closes.
Gotcha.
But it is officially due today. So I encourage you to leave the grace period for issues that might come up. Don't treat it as your due dates. It's only for if you have extenuating circumstances, but the official due dates will always be Tuesday for this class.
Okay.
Yeah. Let's see if I have any new messages here at the bottom. Did I miss something? Oh. Okay, looks like people are contacting each other. Good, good. Yeah, so I'll keep the meeting on a little bit if people need to still figure stuff out. But yeah, reach out to folks. Make sure you get your teams. You get to choose them. Don't forget, you get to choose your own teams, 5 people. And we'll be all ready to rock next week.